This is part 2 of the series Parallel and Perpendicular Lines, and at the end of the last session we began talking about what happens when a line intersects two or more coplanar lines, and we called that a transversal. And we said that these angles that get created are very important angles. So let's go ahead and start this session by looking at those four different angle pairs that are created by a transversal intersecting two other lines. The first one are called corresponding angles. Now note in this picture we have an X in the upper left corner and an X in the upper left corner, but one X is in one intersection, the other X is in another intersection. So this angle is in the same relative position at its intersection as this one is at its intersection. So let's call this the northwest corner, and this is the northwest corner. These two angles are in the same corresponding positions at their relative intersections. So these are called corresponding angles. Corresponding angles are two angles that are in corresponding positions in their relative intersections. Now we could say the same about this angle and this angle. This is in the upper right, so these two angles are corresponding angles. Likewise, this angle and this angle are corresponding angles, and this angle and this angle are corresponding angles. So with one line transversing any two other coplanar lines, we've actually created four separate corresponding angle pairs. So this angle is corresponding to this, this to this, this to this, and this one to this one. So corresponding angles. Now let's look at the next type of angle pair. Here I've highlighted this angle, which is in the lower left of this intersection, and this angle, which is in the upper right of that intersection. Now notice, with our corresponding angles, the angles were on the same side of the transversal. But here, these two angles are on opposite sides of the transversal. Now, if you look at this in a different viewpoint, it may be a little easier to visualize what's going on here. Let's make believe that we're looking at the picture of an ancient Roman ruin, and these two lines are very, very tall walls that you can't climb over easily. So these are big, tall walls, and these are the walls of a fort. Whereas this is a small wall, a little knee-high wall that you can easily step across. Now, we would call this angle inside the fort. This angle would be outside the fort. So all this area here is outside the fort. This area is outside the fort. This area here is inside the fort, and this area here is inside the fort. So we would call this an interior angle. This would be an interior angle. Interior angle, interior angle. This would be an exterior angle. Exterior, exterior, exterior. So in this particular angle pair, we have two angles that are on opposite sides, or we would say alternating sides, of the transversal of this little knee-high wall, and they are inside, in the interior of the fort. So we would call those two angles alternate interior angles. So alternate because they're on opposite sides of the transversal, and interior because they're inside the walls of the fort. Now you could also say that this angle and this angle are alternate interior. So anytime you have a transversal intersecting two otherwise coplanar lines, you set up two pairs of alternate interior angles. This one, and this one, and that one. Alternate interior angles, two angles that are on opposite sides of a transversal inside the two lines. So we'd say these are inside these two lines. Here in the corresponding angles, we had one angle outside, one angle inside, so that doesn't really help us to describe the corresponding angles that way, but alternate interior angles, it should help you to say that these are on alternate sides of the transversal and on the inside. Let's look at the next one. In this picture, I've highlighted two exterior angles on opposite sides of the transversal. So these are exterior angles, and they're on alternate sides of the transversal, so we would call these alternate exterior angles. Just like alternate interior, the description is very similar. Two angles that are on opposite sides of the transversal, but in this case, they're outside the two lines. Alternate interior, inside, alternate exterior, outside. So alternate interior, alternate exterior. And clearly this angle would be alternate exterior to this angle. So here we have two pairs of alternate exterior angles created by a transversal intersecting two otherwise coplanar lines. And now there's one more angle pair, and this one is the oddball. This one is the strange man out. So let's take a look at what this one is. Now here we have two angles that are in the interior but on the same side of the transversal. Now remember, with corresponding angles, we have these two angles on the same side, but notice with these two angles, there's a wall in between the two angles. There's something separating the two angles. Same thing here, there's this wall separating them. Same thing here, there's three walls separating these angles. But here, there's nothing separating them. Now, we've looked at things in the past, in the distant past, that have nothing between them. If you were to take a look at numbers, let's say we took the numbers 1, 2, and 3. These three integers have no integers in between them. These would be called consecutive integers because there's nothing in between them. 1 goes directly to 2, which goes directly to 3, and so on. So these are called consecutive integers. Since these angles have nothing in between them, we call those consecutive angles. So these are consecutive angles because there's nothing between them. And so you can also call these consecutive interior angles. That we really don't have a formal relationship between consecutive exterior angles. There's really no such pair name. So you don't really have to use the interior, but if you want to be formally correct, these are consecutive interior angles. But we're going to use the term consecutive angles to mean these two angles from this point forward. So, consecutive angles, consecutive interior angles, two angles that are on the same side of the transversal inside the two lines. These angles, the consecutive angles, are always going to be the oddballs of the four pairs of angles. There are commonalities between corresponding alternate interior and alternate exterior, and the consecutive always have some different idea attached to them. So one last time, consecutive are the odd ones of the four. Let's go ahead and look at what happens when we have two parallel lines being cut by a transversal. Unlike the last four cases, here we have a situation in which the two lines that were being cut by a transversal are now parallel lines. When we have two parallel lines cut by a transversal, a totally different set of criteria is added to this situation. We still have corresponding angles, but now what we have is some more definitive relationships established between what these angles are. In this case, if two parallel lines are cut by a transversal, each of the corresponding angles are congruent. So each pair of corresponding angles, this angle and this angle, are congruent to one another. That means their measures are the same. Now, it would be fairly easy to show this by moving this line. If you took this line and slid it down to this line, along this line, without changing its orientation, you would see that this angle would stay the same all the way down, and it would overlap directly onto that one. Since these two lines don't separate, this line is parallel to this line, in other words, then these angles would have to be congruent. That's why we call this a postulate. Now, this can be proven when we get to the transformations chapter. You could call this a theorem because it can be proven, but we're going to take this as a postulate. It depends on the author of the text that you look at. Some authors choose to make this a theorem, some authors choose to make this a postulate, but I like to look at this, the corresponding angles, as a postulate because it really is a basic postulate that doesn't really require any proof to see that this is going to be the same angle as that. So this is going to be the basis for all the following theorems that we're going to use for the next set of 3 intersecting lines ideas. Let's take a look at the next angle pair. Now here we have alternate interior angles. If 2 parallel lines are cut by a transversal, then the alternate interior angle pairs are congruent. Now this is a theorem because this one's not quite so intuitively obvious. We're going to go ahead and prove this a little bit later, but this is considered a theorem. But the general idea is we're going to be using this postulate to prove this theorem. But for now, it's important to understand that this angle and this angle are congruent. Also, this angle and this angle are congruent. And so, if 2 parallel lines are cut by a transversal, then each pair of alternate interior angles are congruent. Now, this statement can be abbreviated using a symbol. And the symbol looks very much like this. If you wanted to say the phrase, if 2 parallel lines are cut by a transversal, you could write something like this. This is 2 parallel lines cut by a transversal. So you could say if 2 parallel lines are cut by a transversal, and so on and so forth. So this symbol represents this phrase inside here. So this is kind of a universal symbol that you could draw yourself if you want. And you'll see me doing this often because this is a lot quicker to write than this is. But either way, these mean the same thing. All right, let's move on to the next angle pair. Of course, logically, we have alternate exterior angles, and the alternate exterior angle theorem says if 2 parallel lines are cut by a transversal, then each pair of alternate exterior angles are congruent. So we have a commonality with all 3 of these. Corresponding angles are congruent, alternate interior angles are congruent, and alternate exterior angles are congruent. And now comes the oddball. Remember I said that the consecutive angles are going to be the odd ones? Well, the consecutive angles theorem is different than these 2 theorems and this postulate. So let's take a look at that. In this case, if 2 parallel lines are cut by a transversal, then each pair of consecutive interior angles are supplementary. So this is the odd one. These corresponding angles are congruent, alternate interior angles are congruent, alternate exterior angles are congruent. Consecutive angles are going to be supplementary. Supplementary, remember, means these 2 angle measures add up to 180 degrees. So we're out of the world of congruence when we get to consecutive. So this is the one that's the odd one. And you can kind of see that if you look. You can see that this is going to be an acute angle and this is going to be an obtuse angle. So it's fairly obvious that this angle can't be congruent to this angle because this one's going to be smaller than this one. Likewise, this one's going to be bigger than this one. But it's not a shoe-in guarantee that you're going to remember that. Somehow just come up with an idea because the consecutive are different. The only issues we're dealing with are either congruence or supplementary when we're dealing with these parallel lines and transversals. So this is the other one. All right. Well, what we're going to do now is we're going to prove some of these theorems, and I don't have enough time to do this now, so I'm going to do this at the beginning of the next session. So let's move on to the next session, and I'll talk to you then.